Axial deformation is when a member grows or shrinks along its axis. Usually this is due to forces acting on the member. We use the equation PL over AE to describe this, which is a derivation of Hooke's law, normal stress, and the definition of strain. It helps to break down the member into several parts. First, you want to find any forces that are acting on the member first. Then after that, you will want to have an idea of what the internal forces are going on and at what points. Finally, you will need to make a separate PL over AE equation for each change in cross-section, material, or internal loading. Finally, a prerequisite is that the deformation must be elastic. They cannot be plastic deformation, meaning that the material cannot yield. After yield, the modulus of elasticity is no longer valid and the deformation is different. It will grow at different rates. As I said, the equation for PL over AE comes from the normal axial stress, normal strain, and Hooke's law equations. Here are those equations. When we want to derivate the PL over AE equation, all we need to do is substitute values in for one another. We'll start here with P over A for the axial stress equation and what epsilon is equal to in Hooke's law equation. Then all we need to do is solve for delta, or the elastic deformation, and we get our equation for PL over AE. There are two variations of the PL over AE equation. The first one deals with the summation of all changes in loadings, areas, or elasticities. The integration method is similar, but this is only applicable when the change is constant, usually described by an equation. Now, when we want to break down these equations, we need to break them down so they're easier to solve. We need to follow these steps. First, we need to establish the free body diagram for the object. This goes back to basic statics. Then we need to find an internal force diagram, describing the internal loading at each point along this member. We have already done this in the past, but basically what this is meaning that we need to find where there is a change in the loading inside the material, and we can make a plot to help us understand this loading. Then we need to make a separate PL over AE equation for every change in cross-section, geometry, material, or internal loading. I indicated where these happen on this member, first at the change of material from red to blue, then at the change in cross-section from small to big, and finally in the change of internal loading. We need to keep track of how long that those conditions are true, because that will become the L, or the length that PL over AE is true. And also, finally, if these changes coincide at the same point, you can condense the PL over AE equations into the same equation for those respective changes. This is meaning that when the cross-section and material change at the same point, you do not need two separate PL over AE equations, but that they can be used into just one equation. In this example problem, we are going to work on this member that is loaded axially and is similar to the last problem that we were talking about. Since the statics was already done for us and we know all the force reactions, we can skip that step and go straight to drawing an internal force diagram. Since there is a force at each end and one in the middle, this will actually be pretty simple. We will only have a change at each time the external force is applied. So that means we will have an internal force diagram that looks like this. Finally, we need to make a deflection equation for each change in cross-section, material, and internal loading, which means here and here. Since the change in cross-section and the internal loading is the same point, we can combine those two equations into one equation. Meaning we don't need one equation for the change in cross-section and one equation for the change in internal loading. They will be the same for each. So now we are going to need a cut for the red material and the blue material with the small cross-section and the blue material with the big cross-section. This is also after the change in internal loading, so the cut will coincide with one another. When we write up the equations for each of these sections and then sum them up, we get our total deflection. Remembering that we have a constant internal force and cross-section area for the smaller red and blue sections is important. The only reason why we need a separate equation is because of the material changes. Then what we do is take into account the length that the equation is true. For the red, it would be 4 inches, and for the blue, it would be 3 inches. We then apply the whole process to all 3 sections, and we get our total deflection of 0.000214 inches.